So happy Tuesday to everybody. Let's see, today's class is, today's class is Tuesday, April 21st. We're working on, we need to finish 6.3 and then move on to 6.4. You just finished a nice weekend where you got all caught up on 6.1 and 6.2 and you stressed over the test, and you should have those results at this point, and you should see the points you got in reflected in the Canvas gradebook. You should know exactly where you stand, and the reason I'm saying all of that, you should have solutions to the test as well. And the reason I'm saying that is that last day to withdraw is on Sunday the 26th. So in terms of exercising that choice, you should have everything at your command in terms of where you stand in here and how many points you have. So that's really the only announcement I have. We're ready to continue with 6.3. So that's what we're going to do. We had worked on the idea of what an exponential function is in 6.3. We defined it where the exponent is, the unknown is in the exponent. The base can't be equal to 1 and it has to be greater than 0, so we set up those restrictions on the base. And then we did our first graph and we answered a lot of questions and we found it's one-to-one function. So we looked at y equals 2 to the x and we answered everything. We got it graphed, we had the ordered pairs, we switched them, domain and range, and then we tried to actually formally figure out the inverse functions equation, and we got stuck because when we switched the variables, we ended up with x equals 2 to the y, and we have to solve that for y because that is the inverse functions equation, but it's not written explicitly, meaning that it needs to be solved for y. But we didn't know how to because the y was in the exponent and we've never solved an exponential equation where the unknown is in the exponent. So I just left it blank for now, and we're going to leave it blank until we get to 6.4. So number 2, we're ready for. And number 2 says, all right, let's look at f of x equals 1/2 to the x power now, which is the other way I could pick the base. So that base could either be between 0 and 1, or it could be bigger than 1. So we're going to grab 1/2 to the x power and see what it looks like, and answer all the same questions. So I'm going to do a t-table and take a look at its graph, and then decide if it's 1-to-1, and if it's 1-to-1, then it has an inverse, and then I'll work on that. If it's not 1-to-1, then I'll be done. So if I think about the t-table here, I think the power can be anything I want it to be. It was the base that was restricted. So if I let x be 0, 1/2 to the 0 power, so if x is 0, 1/2 to the 0 power is 1. And if I let x be 1, 1/2 to the first power would be 1/2. If I let x be 2, 1/2 squared would be 1/4. If I let x be 3, 1/2 cubed would be 1/8, etc., etc. I'm going to go pick some negative values now like I did before. So I'll do -1. So now let's think about this. 1/2 to the -1. So again, we're going back to chapter R to think about these ideas. 1/2 to the -1, I'll come over here. We bring that power in, so basically it's 1 to a -1 over 2 to a -1, but they're negative powers, so we play the flip-flop game. So this becomes a 2 to the +1 on the top and a 1 to a +1 on the bottom, and what do I end up with? 2 over 1, which is 2. So think about that. If a whole fraction is to a negative power, you just need to do the reciprocal and take it to the positive power. That's exactly what happened here. The reciprocal of 1/2 is 2 over 1, and now it's to the +1 power. So we'll do it that way because it's quicker on these at least. Or you can put it in your calculator and let it figure it out, but make sure you put parentheses in. I'm going to let x be -2. So if I take 1/2 to the -2 power, that's the same thing as 2 to the +2 power, which will give me 4. And if I put in -3, 1/2 to the -3rd power is the same as 2 over 1 to the +3rd power, so that's going to give me 8, etc. So now I'm going to graph these and see what this function looks like. So I've got 0, 1, and I have 1, 1/2, and I have 2 1/4 and 3 1/8, so it's getting closer and closer to the x-axis over here. And then I have negative 1 2, and negative 2 4, and negative 3 8 here. So this guy is falling on its entire domain. It's a smooth curve. It gets closer and closer to the x-axis, never quite touches it. So this is f of x. I'm going to take a peek for a second because I'm seeing glare and I want to make sure you're not. So it looks like it's okay. I've got the garage light on because it's dark outside. So let's see. So there's f of x. There's y equals 1/2 to the x power. What's its domain and range? So domain and range. So the domain, negative infinity to positive infinity. Negative infinity to positive infinity. Range, y values start at 0 but not quite 0 and go up to infinity. So parenthesis, 0 to infinity. And in fact, there is a HA. There's a horizontal asymptote here, right? The horizontal asymptote is y equals 0. I'll write that down too. And now the next question is it 1-to-1? Because if it's 1-to-1, then I can do the whole inverse thing. So is this 1-to-1? Passes vertical line test, passes horizontal line test. So yes, it is 1-to-1. And since it's 1-to-1, that means that it has an inverse. So I'm going to go figure out the inverse. I'll do it in, I guess I'll use red to look at it. So f inverse, I don't know what the equation is yet, but I know exactly what its t-table is and I can graph it. So its t-table is just the x and y reverse. So 1 0, 1/2 1, 1/4 2, 1/8 3, 2 negative 1, 4 negative 2, 8 negative 3, etc. So let's see, I've got 1 0, that's there, and then 1/2 1, 1/2 1 is here, and 1/4 2, so that's closer to the y-axis. 1/8 3, that's even closer to the y-axis. So I can see this is going to approach the y-axis here. And then I have 2 negative 1, it's about there, and 4 negative 2, about there, and 8 negative 3. That's about here. So this guy looks like this. He's getting closer and closer to the y-axis, and he comes around and goes in this direction. So there's f inverse of x. I'll put my f inverse here. There's f inverse. Now I should make a comment about this f of x. See this guy? It was the 1/2 where the a was between 0 and 1. See this black function here, the original function, now it's inverse. It's the y equals 2 to the x was an example of increasing exponentially. Or growing exponentially, and this is an example of decaying exponentially. So this guy right here, sometimes you'll hear the word something is decaying exponentially. That's where that exponential function is falling instead of rising like the y equals 2 to the x was. So decaying exponentially, sometimes radioactive materials do that. So that's sort of what their functions tend to look like when they're graphed. Let's see, so we're working on the inverse. There's the inverse t-table. There's the graph of it, of its inverse function. And I can do its domain and range. So domain, range. So the red function, the inverse, domain, nothing in for x values until I get to 0, but not quite 0, and then all the way to infinity. So parentheses 0 to infinity. The range, this keeps going down further, so negative infinity to positive infinity for the y values. And again, if I've done things right, I should see the switch here. This should match to this one, and this should match to this one, which it does. And on top of that, because my original exponential function had an HA, my inverse should have a VA, and it does, look, it has a vertical asymptote at x equals 0. So this has a VA at x equal to 0, which is exactly what it should have, just everything reversed. HA into VA, x, the y turns into an x. The only thing I have left now is to come up with the equation of the inverse function. So, because I still have a question mark there, I haven't figured it out yet. And the process to do that is to take, so finding the equation of the inverse function is you take the original equation, which is y equals 1/2 to the x. You switch the variables, so switch the variables, and so this becomes x equals 1/2 to the y. So this is the equation of the inverse function, but it's considered to be the implicit equation. We want it to be the explicit equation, meaning that it is solved for y. So we want to solve this for y, and there's my issue again. The y is in the power, and we have not learned how to solve an exponential equation where the unknown is in the power. How do we write this y equals something? So again, I'm going to say, I don't know. We're going to have to come back to that once we figure things out a little bit more. So we're going to leave that blank as well. So now we have two equations for the inverse functions that are blank. I have one more graph on here on the front side of this, and it's, oh boy, look what it says, graph with transformations. Well, that sounds like a familiar term. Number 3 says graph with transformations, and it's y equals 2 to the x minus 1. They want me to graph this using transformations, and I'm going to do it in the sense of, what does this look like? What base function did we do, brand new one, that looks similar to this? We just did 2 problems before this one. Y equals 2 to the x. So this is y equals 2 to the x transformed. And the question is what's been done to it? So if you recall, when we had y equals 2 to the x, we had a t-table for that. And that t-table said, what did we have here? We had 0, 1, we had 1, 2, we had 2, 4, we had 3, 8, we had negative 1, 1/2, we had negative 2, 1/4, we had negative 3, 1/8. So remember that t-table? I wrote it down really quick. So there's that t-table, the one with y equals 2 to the x. So what's been done to y equals 2 to the x by this transformation? Has it been made skinnier or wider? No, nothing's been multiplied here with the x. Has the x, let's see, has it shifted left or right? That means the x has something added or subtracted to it. I don't see that happening here either. The 2 to the x has stayed the same. What's happened is I've tagged on a negative 1. That tag on of negative 1 means I've either moved it up or down. Which way have I moved it? Down 1. So which value is affected here? The y value is affected. So y is affected by subtracting 1. So this t-table for y equals 2 to the x minus 1, without plugging anything into this, I should be able to do it. The x's are all going to stay the same. So this is, I guess I should, this is x, this is y equals 2 to the x, otherwise I'm going to confuse the issue here. This is x, this is y equals 2 to the x minus 1. I'm using these ordered pairs, I'm going to adjust them. Who's changing? Just the y value. So the x values are all going to stay the same, 0, 1, 2, 3, -1, -2, -3. It's the y values that are going to change, and they're going to change by subtracting 1 from them. So if I take 1 and subtract 1, I get 0. If I take 2 and subtract 1, I get 1. 4 minus 1 is 3. 8 minus 1 is 7. 1/2 minus 1. So 1/2 minus 2/2 is -1/2. 1/4 minus 1. So 1/4 minus 4/4 is -3/4. 1/8 minus 1. So 1/8 minus 8/8 is -7/8. And now I'll graph this. So when I graph this, I now have 0, 0, 1, 1, 2, 3, 3, 7, -1, -1/2, right about there, -2, -3/4, that would be down a little bit more, -3, -7/8. These guys are all less than -1, right? So not quite at -1 yet, but getting closer and closer to a y value of -1. But am I ever going to get a y value of -1? Not quite. I'm just going to keep getting closer and closer to it. So it looks to me like this is y equals to the x just shifted down by 1, which means that instead of the horizontal asymptote being y equals 0, the horizontal asymptote is now shifted down 1. So 0 minus 1 is -1. So the HA is y equals -1 in this case. I think they actually asked that question. They did. There's my first answer right there. And they want the domain and the range, and I should see only the range changing because the only thing I changed was the y. So the domain is still -infinity to +infinity. The range is now -1 and up, just not including the -1. So -1 to infinity instead of 0 to infinity. So even with transformations, they don't change how they work. It has to do with if something's been done to the x value, or if something's been multiplied with the x value, or if something has been added or subtracted at the end. So that's and I'm not going to make the transformations real difficult. I just wanted to bring that idea up again, that sometimes you can think about a transformation to get something graphed, particularly if you know how the original graph looks. I have one more graph on here, which is on the flip side, and there's a little explanation. It talks about this thing called the irrational number e. So e is actually like pi, or like the square root of 2, or the square root of any non-perfect square, or the cube root of any non-perfect cube, etc. It's an irrational number, which means that it cannot be expressed as a repeating or a terminating decimal. And in fact, it's defined as the number that the expression 1 plus 1 over n all raised to the nth power approaches as you let n get bigger and bigger. So in other words, if I let n be 2, I'd have 1 plus 1/2 all to the second power. So basically 1 1/2 to the second power. If I let n be 3, I'd have 1 1/3 to the third power. If I let n be 100, I'd have 1 100th to the 100th power. If I let n be 1 billion, I'd have 1 1 billion to the 1,000,000th power. So as I do that, and as number theory explored that idea, they found this number. They decided to call it E. I believe it was for the person who helped to prove that it was irrational. His name was, sometimes people pronounce it Euler, but it's supposed to be Euler. It's sometimes called his number. It's called E. And I said, first of all, notice this is an exponential expression, which is why it's in this section to start with, because I have an unknown in the power. I have this all being raised to an nth, and I'm changing the n. I'm putting an input and seeing what my output is. And number 2 is, I commented again, as we start to let n get bigger and bigger, which I gave you concrete examples for, we find this number e approaching the number 2.718, it actually goes on. So it's 2.718, 28, 45, 90, blah, blah, blah. It keeps going forever without a repeat or without a termination, which is why it's an irrational number. And in fact, you have an approximation of it on your calculator. So I want you to take out your calculator and let me tell you where the E is. So on your TI-30XIIS, the E key is the third key down on the left. You see where it says, so first there's the second key, then there's the log key, then there's an LN key. Above the LN key, you're gonna see an E with a caret. So above the LN key, so you're gonna see an LN key, and above it, you're gonna see an E with a caret. That's the E key. So what I'd like you to do to get to the E key, you're gonna hit the second, and then you're gonna hit the LN key. And what should pop up is this, and a parenthesis. And it's waiting for you to tell it what power of E do you want. And I just want you to look at E to the first power, in other words, E. So I want you to type a 1 in there and close your parenthesis. So you type a 1 in, close your parenthesis, and then hit enter. And here's what it should be spitting out. It should spit out 2.718281828. It keeps going. Our screen just isn't big enough for it to keep going. That's E. So it is a number. It's a constant. It's irrational, but it's a number. And oftentimes we round it as either 2.7 or 2.72, depending upon our mood or what we want things rounded to. But E is a number. It's an irrational number. So what we're going to do with it is actually take a look at what happens if I have y equals e to the x and see what that graph looks like. And I think you're going to get bored with this one. At least I hope you are. It's mostly just to introduce the idea of an E. So this one says, let's graph f of x equals e to the x. Well, this is an exponential equation or function. The unknown is in the exponent, the x is in the exponent, and the e is not a variable, it is a number. It's just irrational, but it's a number. So this is almost going to be like y equals 2 to the x, but the number's a little bit bigger than 2. So remember, the base could be anything between 0 and 1 or anything bigger than 1. So this base is sort of closer to 3 than it is to 2. So I think it's just going to rise a little steeper. So it's going to be that growing exponentially a little faster than the y equals 2 to the x did. So let's go take a look at this. So I'm going to do all the same stuff again. So I'm going to grab some values. So when x is 0, e to the 0, again, e is not a variable, it is a number. So a number raised to the power of 0 is equal to 1. If I let x be 1, then this is e to the first power, which would be e. But remember, I need to graph this. So now I do need to approximate it. So I'm going to approximate these to 2 decimal places. So I'm going to say 2.72. I'm going to let x be 2. The exact answer is e squared. But remember, I need to graph e squared, so I need some sort of an approximation. So again, I'll approximate that to 2 decimal places. And this guy, when I put it into my calculator, the way I showed you, so you go to second ln, it's going to come up with e caret and a parenthesis. You're going to put a 2 in the parenthesis and then hit equal and round it to 2 decimal places, and you should have 7.39 when you round it to 2 decimal places. I'm not going to go as far as I did with the other ones. I'm going to go to -1 and -2 because I kind of have an idea of how these things look at this point. So if I let x be -1, this is e to the -1, which would be 1 over e. I'm going to put that into my calculator, but actually, I could write 1 over e, or if you wanted to here, you could leave it as e to the -1, because it's easier to put in your calculator that way, because remember, it comes up e with a caret, so inside the parenthesis, you're going to put in a -1, and it's going to spit out, if I round it to 2 decimal places, I get 0.37. Sorry, yeah, And then I'm going to do one more, negative 2. So this would be e to the negative 2, or in other words, 1 over e squared. I'm going to plug it in this way into my calculator because it's easier. And when I do that and round it to 2 decimal places, I get 0.14. So I'm going to go graph this, see what it looks like. I kind of think I know what it's going to look like. It's going to be this guy rising. It's just going to kind of rise a little bit steeper because 2.7 is bigger than 2. So let's see, I've got 0, 1, so here's 0, 1, and then I got 1, 2.72, 1, so that's almost 3, so the other one at 1 was only equal to 2. And then I got 2, and then 7.39, 2, 1, 2, 3, 4, 5, 6, 7, 8, so like almost halfway, almost at 7.5, which is bigger than it was when it was just 2 squared, it was only at 4. So you can see it's rising much more sharply, much steeper. And then falling a little steeper as well. So when x is negative 1, the y value is 0.37, so it's already down here. And at negative 2, it's even closer, 0.14, etc. So here's my f of x, where f of x is equal to e to the x. So very, very similar in terms of domain and range, and it looks to me like there is an HA. So let's see, domain, negative infinity to infinity. The range, again, 0, not including the 0, up to infinity. The horizontal asymptote, again, is y equals 0. And the next question is it 1 to 1? Because if it is 1 to 1, then it has an inverse. So vertical line test passes, horizontal line test, it passes. So yes, it is 1 to 1, which means it has an inverse. So I'm going to go do its inverse function. So f inverse, I don't know its equation yet. I always do that last. It's t-table, it's just the reverse of this. So 1, 0, e1, e squared 2, e to the negative 1, negative 1, e to the negative 2, negative 2. And here's my approximations for each one of those. So I've got 1, 0. 1, 0 is right there. And then I've got e1, which is approximately 2.71. So 2.71 right around here. And then I've got e squared 2, and e squared is approximately 7.39. So 7.4, comma 2, 1, 2, 3, 4, 5, 6, 7.4, 2 right around here. And then I've got e to the negative 1, which is approximately 0.37, and then negative 1. So x is about 0.37, so not very far, and then down 1, so right around here. And then e to the negative 2, which is 0.14, and then a negative 2, so even closer to the y-axis. So here's f inverse. And again, remember, y equals x should be the axis of symmetry, or the function and its inverse are symmetric to that y equals x line. So there's f inverse, domain and range. Let's see, without peeking over here, x values start at 0 but not including it and go to infinity. So parentheses 0 to infinity. Range, negative infinity to positive infinity. And now I'll double check and I'll say, yep, it does exactly what it's supposed to do. And I also noticed there is a vertical asymptote on this one. It keeps getting closer and closer to the y-axis. So my vertical asymptote is x equals 0, which again lines up perfectly with this one. The only thing I have left to do is figure out its equation. And I have a funny feeling I'm going to have the same issue again. So I try to do the equation of the inverse, and so I write down the original, which is y equals e to the x. I exchange the x's and the y's, so I get x equals e to the y. So this is the equation, but it's not in proper form. It's called implicit form. We want it in explicit form. In other words, meaning we want to solve it for y. So we need to solve for y. And I don't know how. Because again, the y is in the power, and we haven't learned anything about how to solve an equation that has the unknown in the power. So I don't know how to do this. All right. Again, I have to think about it. So that, in this section, that's the graphing part of this section. There is one other part of this section, and it has to do with a new rule of exponents, and maybe give us a hint as to how to solve some types of exponential equations. So if we take a look at this new rule of exponents, I'm going to write it up here as well. New rule of exponents, and this is on top of all the other rules that we learned or reviewed back in chapter R. This new rule says that if you have a base, so a is a number, this is sort of like the unknown or the variable possibly. If you have a base to a power and you say it's equal to the same base to a power, so think about that. If I have a base, so I'm going to put a concrete number in here, and it's to some power, I'll make it a squiggle line. And then I tell you it's equal to this same base, and its power is some, I'll make it a star, a different symbol. What's going to have to happen here? If this is 2 to a power, and it's equal to this 2 to this power, well, what do you know about those powers? They have to be the same. So if this is the case, then squiggle must equal star. There's just no other way to do that, and that's what this says. It says if and only if, and I'm going to abbreviate that with an IFF. That's kind of how you abbreviate if and only if. U is equal to V, and the reason it says if and only if is because it goes in both directions. In other words, if I know two things are equal, if I want to, I can put a base down below them and say that they're equal. We don't usually go in that direction. We usually go from left to right in this direction, but it works both ways. And that kind of makes sense. If I have 2 to a power and it's equal to 2 to a power, then those powers must equal each other, or else I can't make that statement. So in other words, if you have same bases equal, then their powers are equal. That's in words what this rule says. And I wrote that down. If you have same bases, if you have same bases equal, then the powers are equal. So this is actually one method of trying to solve an exponential equation. And again, an exponential equation is an equation where the variable is in the exponent. So this is a new type of equation for us to learn how to solve. And this idea of thinking about this rule of exponents basically says this. If you have an exponential equation, one way of trying to solve it is to see if you can create same bases. Because if you can create same bases, then step 2, you can use this rule, drop the base, and equate the powers, which is really, really nice. So that is actually one way to solve an exponential equation. If you can create same bases, then you can drop the base and equate the powers. So I've got 8 examples here, so let's go try these and see what we can do with them. So this first one says 3 to the negative x equals 81. So the first thing I do when the directions say solve is I ask myself, what kind of an equation is it? We know how to solve linear equations, quadratic equations, higher power degree equations by factoring. We know how to solve linear inequalities and quadratic inequalities and higher power inequalities and rational inequalities and rational equations. So we've learned a lot of different things in terms of solving, but what we haven't learned yet, other than this first new rule, is how to solve an exponential equation, which is what this is, because where is the unknown? It's in the exponent. So this is an exponential equation, and the only way we have so far is this brand new idea of if I can create same bases, then I can use this property to drop the base and equate the powers. So the question is, since it's exponential, can I create same bases? If I can't, then I have to have a different way to solve it, which we'll learn later. So right now, you should be able to create same bases, I guess is what I'm saying. So this is a base of 3. Can I turn 81 into a base of 3? And again, even if you think it's obvious what the answer is, I want you to show the work, because as they get harder, they won't be as obvious. So I want you to show the steps and the work and the logic behind using this property, which means create same bases. So I think I can turn 81 into a base of 3. So my first step is to write down 3 to the negative x equals, and I'm going to turn this into a base of 3, and when I do that, it is 3 to the 4th. So now do I have this property? I have 3 to a power, I have 3 to a power. Once I have this property, I can now drop the bases and equate the powers. And it's not until now that I can do this step, because I have the property sitting right in front of me, so I'll do that. So this is what I have, negative x equals 4. Now it's a matter of saying to yourself, what kind of an equation is it now, and how do I solve it? Well, now it's linear. I know exactly what I need to solve this. I hardly have anything left to do. I just need to divide by negative 1. And so I get x equals negative 4, and I'm all done. So solving an exponential equation by trying to create same bases. That was an easier one. Let's go take a look at number 2. So this one, again, when I ask myself, what kind of an equation do I have? Look at where the x is. It's in the exponent, which means it's an exponential equation. And the only way I know to solve an exponential equation right now is to create same bases. What is the base with this power of x? The base is the fraction 1/4. Sometimes you have to deal with fractions, sometimes you don't, but this one probably isn't that bad. Just leave the fractions alone. Don't try to manipulate them. So this is a base of 1/4. So look over here and decide, can you turn 1 over 64 into a base of 1/4? In other words, 1/4 to a power. And I see some of you are nodding your head yes, so let's go try. So I'm going to leave this side alone, and I'm going to turn this side into a base of 1/4. And what power would it have to be raised to get 164? And I hear you saying it had to be cubed to the 3rd power. So now I've written base to a power, and the bases are the same, so I can use this property. I can now drop the base. So drop the bases, equate the powers. So I do that, and I get x equals 3. And then I say, what kind of an equation is that needs to be solved? And you tell me it's already done, and it is. That one was even nicer. So x is equal to 3 on that one. Number 3, okay, so I've got 5 to the power of x plus 3 equals 1/5. This is exponential. The unknown is in the exponent. So right now, only way is try to create same bases. Well, this base is a 5. And this number over here is a 1/5. Somehow I have to try to think about, can I turn 5 into a base of 1/5 to a power? Or maybe can I turn 1/5 into a base of 5 to a power? In other words, leave this 5 alone. Can I turn this into something that says 5 to a power? So I've got 5 to the x plus 3 equals, I want to write 5 to a power. So tell me, what is 1/5 if I write it 5 to a power? So think about this. Right now, this 5 is to a power 1 in the denominator, but if I unsimplify it and bring it up, it's going to be 5 to the negative 1, right? So I'm going to rewrite that as 5 to the negative 1. I'm sort of going to unsimplify it because I know we don't like to leave negative powers, but it becomes handy for me to be able to do that to solve this. So now I have the property. 5 to a power equals 5 to a power. You've got to show that step. So I can see that you got same bases, so you can drop the base. So you can drop bases and equate the powers. I'm going to stop writing that. So what do I have here is x plus 3 has to equal -1. Now what kind of an equation am I solving? It's linear. I know what to do. I just need to subtract 3. So I get x equals -4, and I've got it. I'm all done. So that one hopefully still wasn't too bad. Let's go take a look at number 4. Come back over here. This one says 4 to the x squared equals 2 to the x. What kind of an equation do I have? Exponential. The unknowns are all in the exponents, and all it takes is one unknown to be in an exponent to make it exponential, so to speak. So it's an exponential equation. I'm going to try and create same bases. The base here is 4. The base here is 2. So can I turn both of these into a base of 4? Can I turn both of these into a base of 2? I think I can. So in other words, this side is okay. It's this side that I need to manipulate. So tell me, how do I write 4 so it's a base of 2? And you're going to tell me 2 squared, right? But that 4 is being raised to a power, isn't it? So that means this 2 squared is going to be raised to the power of x squared equals 2 to the x. Don't leave me hanging here. I need this equation to look like the rule for exponents that says if you have same bases equal, then you can drop the base and equate the powers. I do not have same bases equal yet. This does not say 2 to a single power yet. It says 2 to a power raised to another power. So now we go back to chapter R. What do you do when you have a power raised to a power? What do you do with the powers? I think I heard it. You multiply them. So this is going to become the base of 2, and the new power is going to be 2 times x squared, which is 2x squared. This side says 2 to the x. Now you have same bases, so now you can drop the base and equate the powers. So when I drop the base and equate the powers, I get an equation that says 2x squared equals x. What kind of an equation is this? Yeah, now this is quadratic, right? Which means I have 4 choices on how to solve this. I can put everything on the one side equal to 0 and try to do the 0 factor property, or I could do the quadratic equation. Square root property is not going to work, and because there's an x in it, and I don't want to complete the square if I don't have to. So I'm either going to put everything on the left side equal to 0 and try and factor, or I'll use the quadratic formula, one or the other. Here's something that I want to comment on. For some reason, when it's written like this, students are very tempted to do this thing where they divide both sides by x. And I'm not quite sure where that came from. I had one student tell me once that his teacher told him to do that, and oh boy, I sure hope not. You cannot divide both sides of an equation by a variable. You just can't. You can divide both sides of an equation by a number that you know, like I divide every term or both sides by 2, or every term or both sides by 3, or by -1, or as long as it's a number. But you can't divide both sides of an equation by a variable because you don't know what the variable is. And if that variable happens to be 0, then you have a problem. So do not do that. This is quadratic, so you have one of 4 ways. So I'm going to bring the x over. 2x squared minus x equals 0. I think I'll just do the 0 factor property because I can see this has a GCF. I'm going to factor out the x and get 2x minus 1 equals 0. This plays a part in the answers because it's a variable, and then this will play a part. There's going to be my 2 answers. This one gives me x equals 0, or this one gives me x equals 1/2. So 2 solutions to this one. Both 0 work and 1/2 works. So now let's go take a look at number 5. see what we can do with it. So again, the directions say solve, so I have to decide what kind of an equation it is, and I notice unknowns in the unknown in the exponent. So as a result, it's an exponential equation. So I'm going to try and create same bases. The base here is 9. The base here is 27. Can I turn 27 into a base of 9? So I see some of you shaking your head, yes. How? 9 to what power gives you 27? I know you're thinking 9 times 3 is 27. That's not to a power. Base is something raised to a power. Can I take 9 and raise it to a power and get 27? 9 to the first power is 9. 9 squared is 81. I'm already too big. So I cannot turn this into a base of 9. Can I turn the 9 into a base of 27? No, you can't go backwards. So now I'm thinking, uh-oh. So now you have to think a little bit further. Sometimes you have to change them both. So the question is can I turn both 27 and 9 into the same base that isn't 9 or 27, but actually works? So think about this. 9 has a base of 3 in it, and so does 27. So I'm going to convert both of these. So this 9 is 3 squared, but that 3 squared is being raised to a power of negative x plus 15. This 27 is 3 cubed, but that 3 cubed is being raised to a power of x. So they're getting a little more difficult now. So this is 3 squared to the power of negative x plus 15 equals, this is 3 cubed raised to the power of x. So again, I can't leave it like this. These are not same bases. This one is a base of 3 squared, and this one is a base of 3 cubed, I guess. But I need to get rid of the parentheses. In other words, I needed to say 3 to a power equals 3 to a power in order to use that property. So again, what did you tell me? If you have a power raised to a power, what do you do with the powers? You multiply them. So I have to take 2 and multiply it with this, which means I'm going to have to do what? Distribute the 2, right? So this becomes 3 to the power of a negative 2x plus 30. 2 times negative x, 2 times 15. This one becomes 3 to the power of 3 times x, which is 3x. Now I have the property that says same base is equal, drop the bases, equate the powers. So now I can drop the base and get negative 2x plus 30 has to equal 3x. What kind of an equation do I have now? It's linear. I know what to do here. I'll add 2x, I'll get 30 equals 5x. I'll divide by 5, and I'll get x equals 6. And I've got my answer. It was a little more complicated, but I was able to do it by using the new property that we have about same bases being equal. So number 6. So I'm trying to solve this, and again I notice it's exponential, so I'm going to try and create same bases. This is a base of 5, and this is a base of 125. It's got 5s in it, right? So I'm going to leave this one alone. 5 to the x squared plus 8 equals 125 is 5 cubed. And then that's being raised to the power of 2x. So one more step before you drop things. This says 5 to the x squared plus 8, and this actually says 5 to the power of 6x. Now you can drop bases and equate powers, because I have same bases equal, so that means x squared plus 8 equals 6x. Again, I want to see the work to get to this line. Don't jip me on this one. And now I'm going to solve this. What kind of an equation is this now? It is quadratic. I should be getting 2 answers here. So let's see, this looks like, I'm going to try and factor it. I think I'm going to bring my 6x over. So x squared minus 6x plus 8 equals 0. It's easy big X, there's no GCF. Multiply to 8, add to negative 6. Let's see if I can get this to work. Negative, I think they both need to be negative. Negative 4, negative 2 multiplies to 8, adds to negative 6. That was nice. So this is x minus 4 minus 2 equals 0. So this one gives me x equals 4, or this one gives me x equals 2. So there's my two solutions for that one, 4 or 2. And can you check these? Sure, if you want to. You put them in and see if they work. They should. So let's see, let's go take a look at number 7. I do like this one, okay? Just commenting. So let's see, 9 to the power of 2x times 27 to the power of x squared equals 3 to the negative 1. Oh my. What kind of equation is it? It's exponential. The unknown is in the exponent, there and there. How the heck do I do this one? So can I just take like 9 times 27 and I don't know, add the powers or something? Do we have a rule back in chapter R that said I could do that? What was that rule back in chapter R? It said if you have same bases multiplying, then you keep the base and add the powers, right? So if I had x to the 3rd times x to the 4th, that would give me x to the 7th, right? But that was only if I had same bases multiplying. Are these the same base that are multiplying? So there's nothing you can do here yet other than to look at these and think about creating same bases. This is a base of 3, a base of 27, and a base of 3. What would be a good choice for all having the same base? I think I can all turn them all into bases of 3, right? So let's see. This 9 is 3 squared, and it's raised to the power of 2x times, well actually I'm going to put it in parentheses anyway, so I don't really need the times sign there. 27 is 3 cubed, and it's raised to the power of x squared. And this, I get to leave that one alone. That one's already ready to go with 3 to a negative 1. I'm still not there yet, okay? This needs to say 3 to a power, 3 to a power. This wasn't 5x cubed times 2x to the 4th. It was just this exact same base. I have to have exactly the same base. So what does this really say? If it's 3 squared raised to the 2x power, it's actually 3 to the power of 2 times 2x, which is 4x. And that's multiplying with, I'll put my dot back in now, 3 to the 3rd power raised to the x squared power is actually 3 to the power of 3 times x squared, which is 3x squared, equals 3 to the negative 1. And don't jip me on the lines of showing work on this either. Now what can I do? Now I have same bases multiplying, and the rule says if you have same bases multiplying, you keep the base and you add the powers. So I'm going to add 4x plus 3x squared, and that equals 3 to the negative 1. Now does it follow the rule of the new exponential rule, which says same base is equal, drop the base, equate the powers. 3 to a power, 3 to a power. So now I can drop the base and equate the powers. So this says 4x plus 3x squared equals negative 1. What kind of an equation do I have? It's quadratic. So I'm going to go try and get it all on one side and see if I can factor it. And if I can't, then I'll use the quadratic formula. I'm going to write it in good form. So I'm going to write 3x squared plus 4x plus 1 when I bring it over to the left equals 0. There's no GCF, 3 terms, so maybe the hard big X if I can get it done. 3 times 1 is 3. Multiply to 3, add to 4, that would be 1 times 3. Multiplies to 3, adds to 4. Either rewrite this and use grouping, or if you do the simplify method, you just put a 3x over each one of these and simplify. Can't simplify there, but here I can simplify into an x and a 1. So this is 3x plus 1. X plus 1 equals 0 when I get it factored. And two solutions, x equals negative 1/3 from this first one, or x equals negative 1 from the second one. So a little trickier, a lot of remembering all my exponential rules on top of the new one that we're using to actually solve these things. I've got one more of these. Oh, it's got an E in it. What's e again? Is e an unknown? Is e a variable? It's a number. It's an irrational number. So let's see, I've got e to the power of 3x equals e squared over e to the x. So this is very definitely an exponential equation because the unknown is up here in the exponent in a couple places. E is a number. It's an irrational number. So the base is e, right? I don't think I can change that. E is an irrational number. I'm not going to be able to turn it into any other base. So this base is e to the 3x. So this side is ready to go. If I can just get this side to say e to a power. So what do we have going on here? E to a power over e to a power, right? So what's the rule? When you have same bases dividing formally, what's the rule? I know oftentimes we just say who has more, how many more, but what does that mean we're doing? We're keeping the base and subtracting the powers, right? Numerator power minus denominator power. So this is e to the 2 minus x on the right side. So nice thing to remember, that rule from a long time ago. And now look, same bases. I'm ready to drop the base and equate the powers. So I drop the base, I equate the powers, 3x equals 2 minus x. What kind of an equation is this? This is linear. I know exactly what to do. I'll add x, I'll get 4x equals 2, I'll divide by 4, and I'll get x equals 1/2, and I'm all done. So solving these exponential equations by trying to create a same base. If I can do it, it's usually the easier way to go. If I can't create a same base, then I'm going to be stuck and I'm going to have to try a different way, which we haven't learned yet. But now, you know, we solved all these exponential equations by creating same bases. Maybe that's what I needed on those 3 inverse functions that we couldn't figure out. Remember that first one? So let me think about this again. We had y equals 2 to the x, and then we switched them, right? And we wrote x equals 2 to the y. That was that very first one. And we tried to solve for y. Well, this is an exponential equation. So if I can create same bases, I can drop bases and equate the powers. The base here is 2. Is there any way I can turn that into a base of 2? I don't think so, because I don't know what x is either. Darn. Alright, so I'm still at a haven't figured it out yet. Darn. Okay. So we just finished 6.3. We're going to go look at 6.4 now, and then maybe we'll be able to figure that out. So I'm going to grab 6.4's notes here. So I'm going to erase all this stuff. Are you having fun yet? Some of you are shaking your head yes. I can see it. Alright, so 6.4. Oh, look what 6.4 is called. Logarithmic functions. Logs. So we're finally going to get to that stuff on logs. So I wrote at the top of this, remember when we had y equals a to the x, and we put specific numbers in there like 2 and 1/2 and an e, and we said that that base has to be greater than 0, not equal to 1. So we put restrictions on the base, and it was a 1-to-1 function, so it had an inverse, and we even switched the x and the y variables to try and write the equation, but we got stuck. So again, remember, we got stuck at the x equals 2 to the y. So we're going to define our way out of it. Interesting, mathematicians define their way out of this. And they defined a logarithm, and they defined that logarithm. It's just a way, it actually was defined purposely to be a way of writing the inverse of an exponential function. And they said that if a to the y is equal to x, then, and I know it says if and only if because it goes in both directions, but I'll just write if and then. If a to the y is equal to x, then y is going to equal log base a of x. Oh boy. So in other words, they define their way out of solving this for y by defining what's called a log function, so that they could write it y equals instead of having it implicitly described in this way without it being solved for y. So take a look at the pieces here. And this is one of the first things that students get concerned about with logs, is notice there's an a, a y, and an x. An a, a y, and an x, and then the word log written in there. How do the pieces of the puzzle fit together? In other words, this is exponential form, and this is log form. So this is exponential form. This is log form. They are equivalent. So if you have an exponential equation, you can always write it in its equivalent log form by this definition. How do the pieces of the puzzle fit together? We'll notice that the base in this exponential form is actually the base of the log as well. So this is read log of base a of x. And in fact, if you were in first grade or whatever learning to write on a line, just so you know, because students tend to write these all goofy ways, the line is there. So the tail of the G and the base go slightly under the line, but everything else is in line with each other. So notice the base of this exponential equation is the base of the log. The power or the exponent of the base is actually the answer, and the answer is now what's called the argument of the log. And so I wrote down next to this, I said that the a is still the base, and it's still greater than 0, not equal to 1. This is the base of not only the exponential equation, but of the log as well. And then I also commented now, I wanted to remind you, the x is greater than 0. So remember this, when we were looking at this inverse function, what did we find out about the domain of that inverse function? It's on my other piece of paper. The domain of the inverse function was 0 to infinity, not including the 0. So guess what? The domain of the inverse function has become what's called the argument of the log, which means that the argument of the log needs to be greater than 0. It's called an argument. I guess the log is having an argument with something, but anyway, that's called the argument of the log. So two good pieces to know in terms of log functions. A base of a log is going to be greater than 0, not equal to 1, always, so it has restrictions on it. And the argument of the log, the thing that the log is of, not multiplication, it's just what you're taking the log of, the argument needs to be strictly greater than 0. So what I'd like you to do is take out your calculator again for a second. And I want you to go find the log key on here, which is the second key down on the left. And I want you to hit it. And what's going to come up is you're going to see a log, and then it's going to put a parenthesis, it's going to tell you to put a number in there. And I want you to put in a number, let's put in 10 just for the heck of it. So we'll put in 10 and close your parenthesis and hit equal. And it spits out 1. This is a valid argument. It's greater than 0, okay? Does anybody know on your calculator what the base is? Notice I didn't write a base in. Does anybody know what the base is on your calculator and the key in your calculator? Yes, 10. Good. I usually have a few students who know this from science class. It's an understood base 10 on the calculator. Let's go push that log key again, and let's put in 0 this time and see what happens. So if you hit your log key and then you put in a 0, what does it say? It says domain error. It's telling you, you have an issue with the domain. The fact is the domain needs to be, or the argument needs to be greater than 0, or else you're not going to be able to compute it. And so that'll happen, and then you'll know you have an issue, and you need to try again because you put in a bad number for the log. Let's see. So then I talk about this thing called, I talk about this thing called the natural logarithm, and the natural logarithm is what's called ln is usually the symbol that we use for it, and you have an ln key on your calculator. It's below the log key. Remember the e to the power was above it. So again, go hit your ln key for me, and it'll come up like this. And then it'll put a parenthesis, and I would like you to put a 0 in there and see what happens. I think you're going to have a problem again, right? Ah, domain error. Okay. So it applies both for any log. It doesn't matter, natural log or log, which is on your calculator base 10. Does anybody know what the base is on a natural log? Guess what? It's a base of e. So there's that e again. It comes into play. So I wrote down natural logarithm. Natural logarithm comes from the idea of e to the y equals x. So natural logarithm is coming from e to the y equal to x. And if e to the y is equal to x, then the log form would be, so think about this now. Our log form was, we said that the y would be the answer, and then we would have a log, and the base would be the base of the log, and then the answer would become the argument of the log. But notice I didn't write it that way. Look at what I wrote. I wrote y equals ln of x. This is just a shortcut way of writing log base e. So when you see ln of x, it means log base e of x. And it's just easier to write that way. Scientists like to write it that way because then they know it's a base e and they don't have to write it down. They just automatically know that's what it is. Again, the argument needs to be greater than 0, and the base needs to be greater than 0, not equal to 1, which e is both of those things. And then the last one is that common logarithm, which we kind of talked about on your calculator as well. So it's called a common log, and it comes from the idea of 10 to the y equals x. And if that's the case, then if I rewrite that in log form and solve it for y would equal, so I'd have a log, the base here would be the base of my log, and the answer would be the argument of my log. So y equals log base 10 of x. And notice, I didn't write it this way, I wrote it like this, log of x. I left the base off. This means this. It's just a shortcut way of saying that we have a common log, which means the base is 10. So if you see log without a base, it automatically means it's base 10. And if you want to write the 10 in because it helps, then do it. If you see ln of x, it automatically means it's a log base e. But honestly, we usually don't rewrite that. We usually leave that as an ln and just understand that that means a base of e. So what I'd like to do is get a little more practice going from exponential form to log form or log form to exponential form. And actually, I've got like 6 examples for that, but you know what we need to do first? We need to go back to those 3 inverse functions and write them. So let's go fill those 3 inverse functions in first, and then we'll go look at these 6 examples. So we need to go back to, that's from the section before, where we had our inverse function. We didn't know what it was, but it was coming from, we had y equals 2 to the x, and then we did the inverse, and we were trying to come up with the equation. So we were trying to come up with the equation for the inverse of this. So we switched the x's and the y's, and we wrote x equals 2 to the y. And then I said, solve it for y. And I said, I don't know what to do. And then I thought, oh, maybe we can create same bases because this is exponential. This is a base of 2. There's no way to turn x into a base of 2. So we can't do it that way. But now we have another way to do it. If it's exponential form, I can always write it in log form. And the question is how do I go from this to log form? We're trying to solve for y, so we write y equals, we write the word log. The base of the exponential form is the base of the log, so I put a 2 here. And then the answer of the exponential form is the argument of the log. So solved for y, x equals 2 to the y, says y equals log base 2 of x, which means that f inverse, this is my f inverse, so f inverse is equal to log base 2 of x. So that's what that red graph is. It's log base 2 of x. So we also had an f inverse that we had a question mark on, and it came from, so we had an equation for the inverse that we were trying to find, and it was y equals 1/2 to the x, I believe. And we switched, and we wrote x equals 1/2 to the y, and then we needed to solve for y, and I wrote, I don't know. And then if you try to make same bases to use that rule, I can't turn x into a base of 1/2, so that doesn't work. So the next best thing is to take this exponential form and turn it into its equivalent log form by definition. So that the log is a definition. So how does this turn into log form? Solving for y, the power now becomes the answer, so to speak, and then I write a log. The base is the base of the log, so I write a base down there with the tail of the g. The argument of the log is what used to be the answer, which is the x. This is the inverse function now solved for y. So f inverse of x, that's the y part, would equal log base 1/2 of x. That's the inverse function's equation. And we had that one last one, which was, we didn't know what f inverse was, but we knew that the equation that we started with was y equals e to the x. We switched things because it had an inverse, we got it graphed, we just needed its equation, so we switched x's and y's, and we got x equals e to the y, and then we needed to solve for y, and I said, oh, I don't know what to do, and then we got that rule that said same bases equal, then you can drop the base and equate the powers. Well, this is a base of e, there's no way for me to turn x into a base of e, so I can't use that property. So now I can use the definition that relates an exponential equation to a log equation, and it says that the exponent becomes the answer, so y equals, I write down log, the base of this exponential equation is the base of the log, so log base e, and the argument is what used to be the answer, so y equals log base e of x. Or in other words, what's a shorthand way of writing this? Y equals, if I have log base e, that's just the natural log of x. So this is my inverse function. The f inverse is the y part, and it's equal to ln of x. So there's my equation for that one. So just using this definition of log actually makes it so that I can write the inverse equation. Okay, so now we can go and look in more detail at this process of what exactly we're doing to switch things around from exponential notation to log form, exponential form to log form. So let's go practice that a little bit more. I'm going to do a little sort of picture mnemonic to help you if you're still struggling with where the pieces fit. So I've been just using words up until now, but I'll show you one more thing you can look at. Boy, is the red hard to get off. But then I noticed watching the video the green is a little bit hard to distinguish, or at least I thought it was. So. Alright, so it says, rewrite 1 to 6 in either log form or exponential form. So I'm actually going to write exponential form and then log form. Number 1. So number 1, which form have they written this in? This looks like exponential form to me because I don't see the word log anywhere. So number 1 says 2 to the 5th equals 32. That's exponential form. And they want me to write the equivalent log form for it. Well, first of all, is this a true statement? 2 to the 5th does equal 32. So now how do I write this in its equivalent log form? So I'm going to actually write it with the log first. I'm going to leave some space for a base and an argument and then an answer. So now let's think about the words for a minute. The base of the exponential form is the base of the log, so that goes there too. And then remember that the power here was actually the answer, so the 5 must come here. And the answer here was the argument of the log, so the 32 goes here. And again, this is all on the same line. Nothing's raised up higher than anything else. Just the G's tail and the 2 are down below. So 2 to the 5th equals 32 is the same as log base 2 of 32 equal to 5. This is log form of the equation, exponential form of the equation. We use the words to fill in the pieces, but there's another sort of a cute little picture thing to help you to remember. I sort of draw a little circle here. So if you take 2 as a check, if you take 2 to the power of 5, you'll get 32. And there it is, 2 to the 5th equals 32. So this little circle can kind of help make sure that you've put the pieces of the puzzle in the right places. So number 2, which form have I given it to you there? That's log form, right? Number 2 says they gave me log. They said log base 5 of 1 equals 0. And I should comment. See over here? You go, well, can't I just check that in my calculator and make sure? What is that log key in your calculator? The LOG key is base what? 10, and 10 only. This is base 2. You cannot put in log of 32 in your calculator. It's not going to spit out 5 because it's calculating log base 10 of 32, not log base 2 of 32, which is what you want it to calculate. So that isn't going to work. This one, also, you cannot put this in your calculator. Well, I shouldn't say that, but the LOG key in your calculator is base 10 only. The fact is that log of 1 is always going to be 0, but in general, putting this in your calculator, it's not going to check. But anyway, here it is in log form. I don't know if it's correct yet or not, because technically I can't put this in my calculator, but if I rewrite it in exponential form, I sure can check it. So in exponential form now, what does this say? Here's where the little circle thing really helps. So in exponential form, or in words, the base of the log would be the base of the exponential form. The power is the answer, which is the 0, and then the argument is the number on the other side, which is the 1, or the answer, in other words. But in terms of the little circle, just think about this. 5 to the power of 0 has to equal 1. 5 to the power of 0 equals 1. Is that a true statement? Yes, it is. So because that's true, I know this is true even without checking it on my calculator. Or being able to check it on my calculator. So the third one, what did I give you? It looks like I gave you exponential form on this one. 16 to the 1/4 equals 2. First of all, is that a correct statement? So let's think about that for a minute. What does 16 to the 1/4 mean? What does a 1/4 power mean? Oh, back to chapter R again. It means the 4th root of 16 to the 1st power. So the 4th root of 16. What's the 4th root of 16? It's 2, right? 2 times 2 times 2 times 2 will give me 16. So this is a true statement. So now I'm going to convert it to its equivalent log form, which means that I'm going to have a log. The 16 is the base. And if you want to, you can use the picture to help you right at the beginning. I'm going to get rid of all my little cheat things here to make room. So this says 16 to the power of 1/4 equals 2. So you write a log, you leave space for a power and a base, you write an equal sign, and then the base of this is the base of the log, and then do the little circle thing. This 16 is to what power? 1/4. So the 1/4 comes over here, and it's equal to what? 2. So the 2 is the argument. So you can always do that even when you're filling things in. So 16 to the 1/4 power equals 2, and then I just get rid of the little mnemonic device I used, or the picture I used, and there it is. 16 base 16, log base 16 of 2 is equal to 1/4. So number 4, which form did I give that one to you in? So 4 is in log form already. So log base 27 of 3 is equal to 1/3. So that one I can't really check on my calculator because I can't, if I put in log 3 in my calculator, it will be calculating log base 10 of 3, which is a completely different answer than this one. So the only way I can effectively check this is to rewrite it in its equivalent exponential form. And in exponential form, this says 27 to the power of 1/3. 27 to the power of 1/3 has to equal 3. So 27 to the power of 1/3 has to equal the 3. Is that a true statement? So again, what does this mean? This means the cube root of 27 and the cube root of 27 is 3. So I can see that that's a true statement, and my log, I've got both ways, exponential form and log form. Number 5 is exponential form, and it says e to the x equals 12. So written in log form, I'm going to have a log. I'm going to leave space for a base and an argument. So the base is e, and it's e to the power of x, so the x is coming over here, has to equal 12, so the 12 is the argument. E to the x equals 12. So what's the shortcut way of writing this? Or log base e is just ln, so ln of 12 equals x is what that says. And the last one, number 6, I've got this written in log form, so I have log base 3 of 5 equals x. They want me to write it in its equivalent exponential form. So let's see, I can't put this in my calculator, so I'm going to just use my rules here. 3 to the power of x. 3 to the power of x has to equal the argument, which is 5. Again, 3 to the power of x equals the 5. And there it is. There's no way to check this because I have an unknown in there, just like here I had an unknown as well. But getting used to going back and forth, log form, exponential form, we will use this to help us solve equations quite a bit. So it's useful to be able to manipulate and go back and forth. So the next 2 questions are a little bit different. They are asking me to find an exact value of something, which means they don't want me to round. They just want it written in exact form, even if it's not a nice form and I don't really know what value it would be. They want it to be written in as an exact answer, no rounding. And what they say is, they just give me the log. They say log of base 1/3 of 9. And instead of trying to eyeball this, because I know some of you might be able to do it, I'm going to ask you to do it formally, which means they want me to say what this is equal. So in other words, this is equal to some value, so I'm just going to call it x. And so I would like you to write it as an equation and just say they're trying to get me to figure out what this equals, so it's equal to some x. And now the question is how do I solve this? So so I've written this as a log equation, and I'm going to rewrite it now in exponential form and see what it looks like. So in exponential form, because this is log form, this says 1/3 to the power of x has to equal 9, right? 1/3 to the power of x equals 9. So do the little circular thing. Here it is in exponential form. So this was a log equation that I didn't quite know how to figure out because I can't put it into my calculator. So I'm going to rewrite it in its exponential form and see if I can solve that. Well, what kind of an equation is this that I just created? It's exponential, right? The unknown is in the exponent. And the only way we know how to solve those is to either rewrite it in log form, which won't do me any good, I'll just get back to here, or maybe try to create same bases. So this is a base of 1/3, and this is 9. Oh boy. So I can't turn 1/3 into 9. I could turn 1/3 into a 3 to a power, and the 9 I can turn into 3 to a power, so I think I can create same bases. Tell me about 1/3. 1/3 is the same as 3 to the -1. So this is 3 to the -1 to the power of x equals, this is 3 squared. I don't have same bases yet. Finish this. Don't just assume you're okay. Get it to look like that property. This is actually a base of 3, and the power is, I multiply those two and I get -x equals 3 to the second power. Now I have same bases. Now I can drop them and equate the powers. So -x equals 2. This is linear. I can solve it. I divide by -1. I get x equals -2. And I'm all done. So notice I took a look at that. And the reason I did was I wanted to see where the x was. It was over here. Because remember, we have restrictions on bases of logs and arguments. But I knew what those both were. So it looks to me like, so what does this mean? This means that the log base 1/3 of 9 is equal to -2. We just figured it out. This is equal to x. We said x is -2, so log of base 1/3 of 9 is equal to -2. So we actually found the exact value of that without a calculator, because our calculator isn't going to be able to do log base 1/3 anyway. Then they want me to find the exact value of log square root of 10. Now this one, notice, what's missing here is the base, which means the base is what? The base is 10. So I could put this into my calculator, and I bet you if you put this into your calculator, it spits out 1/2. It'll spit out 0.5. You can check me and see. So how did I figure that out? Well, I kind of did a little bit in my head here. But this is a base of 10, so I'm going to write it in for ease. And we're trying to figure out what this is equal to, so I'm going to write down it's equal to some x. I don't know what x is. And short of knowing I can put this in my calculator, I'm going to formally solve this instead. So I'm going to rewrite it in its exponential form and see what it looks like. So this says 10 to the power x has to equal the square root of 10. 10 to the power of x equals the argument, which is the square root of 10. What kind of an equation is this? It's exponential. So I'm going to try and create same bases. This is a base of 10. Can I turn this into 10 to a power? I think so. This says 10 to the x. This is 10 to the what power? 1/2, 1/2. Same bases, equal, drop the base, equate the powers. X equals 1/2. It's already solved. So what does this mean? This means that my log of square root of 10 is equal to 1/2. And I've got my answer by doing it formally. I didn't cheat and put it in the calculator, although I could have on that one. So now we're going to skip to a different kind of a problem here. Number 9 says they want me to find the domain. Oh boy. So here's my function. And they want me to find the domain. Domain is what again? All possible x values, right? Well, where are the x's here? This is a log equation, right? And where are the x's? Are they in the base of the log? No. Are they in the argument of the log? Yes. So now I have to think about restrictions on a log. So what are the restrictions on a log? So restrictions on logs are the base needs to be greater than 0, not equal to 1, right? That's the A, greater than 0, not equal to 1, but we know what that number is, it's fine. The argument of the log, I'm going to call it the arg. I'm going to be a pirate. The argument of the log needs to be what? Greater than 0. Remember we put in log of 0, it didn't work. Log of a negative number, it didn't work. The argument needs to be greater than 0. So this is all in the argument. So the restrictions here are right here. Argument, so domain. Argument needs to be greater than 0. So what is the argument? The argument is x plus 3 over x. Needs to be greater than 0. So I need to solve this. in order to figure out what my domain restrictions are so I can answer this question, how do I solve that? That's an inequality, right? How do I solve that inequality? What kind of an inequality is that? Is it linear? I don't think so. We've got x's and denominators here. It's not linear, it's not quadratic. It is a rational inequality. You just got tested on this. This is a rational inequality. How do I solve a rational inequality? I pretend it's an equation and I find all the critical values, right? So where are the critical values coming from on a rational inequality? They're coming not only from pretending it's an equation, but they're also coming from domain restrictions on the rational function that's sitting here. Oh boy. So let's see, I'm going to pretend it's an equation. So it says x plus 3 over x equals 0. And now I'll solve this, so I'll multiply both sides times x. I'll get x plus 3 equals 0. That gives me x equals negative 3. So there's a critical value. But what else is a critical value here? Is the domain restriction, which is also x equal to 0 is a critical value because you have a domain restriction here that x can't equal 0. So this is coming from domain restriction. So then what did we do? Once we found the critical values, we made a number line of the critical values and we did test points. Negative 3 and 0. So I've got 3 test points I need to do. So I need to do a test point of, test point of something smaller than negative 3, so I'll do negative 4. So let's see, negative 4 plus 3 over negative 4, is that greater than 0? So let's see, that's negative 1 over negative 4, is that greater than 0? That gives me positive 1/4, so yeah, that works. Now I'll pick something between negative 3 and 0, so test point, I think I'll grab negative 1. So I've got negative 1 plus 3 over negative 1, is that greater than 0? So that's 2 over negative 1, is that greater than 0? No, that's negative 2, and that's definitely not greater than 0. And then I'll pick a test point bigger than 0, so I'll pick 1. So I've got 1 plus 3 over 1, is that greater than 0? So that's 4 over 1, yeah, that is, 4 is greater than 0. So that means for the argument to be greater than 0, it either needs to be from negative infinity to negative 3 or 0 to infinity. So this is my domain. My domain then is going to be, because this is what the argument needs to be for this to satisfy the restriction. So my domain needs to be anything from negative infinity to negative 3, not including the negative 3 because it's strictly, the argument strictly needs to be greater than 0, so don't include it. And then union, I go from 0, not including the 0, to infinity. So any of these values will work in this argument. Anything else will give me a negative answer in that argument, and then I'll have a log of a negative, and that'll be an issue. So finding the domain of a log can be a little tricky, depending upon what its argument looks like. So we've got one more of these, number 10. Again, they want me to find the domain, and this time the function says log base 7 4x squared. Alright? So they want me to find the domain, which means I need to think about where's the x here? It's in the argument again, isn't it, of a log. So logs have restrictions. The restrictions on a log is that the argument needs to be greater than 0. So that means this 4x squared needs to be greater than 0. So 4x squared needs to be greater than 0. So that's what I need to solve here. So what kind of an inequality is this in terms of solving this? This looks like a quadratic inequality, right? So how do I solve a quadratic inequality? I pretend it's an equation, I get critical values, and I do my little test point thing. All right, so fine, I'll pretend. So again, this is my domain restriction here on a log. The argument has to be greater than 0, so I took the argument, made it greater than 0, and then I have to think about how to solve this. So I'm going to pretend this says 4x squared equals 0, and I'm going to solve this for my critical values. And this is quadratic, and I can divide away the 4, so the only thing that's playing a part here is the x squared, and I should get 2 answers, but they're both going to be what? 0, right? So x is 0, x equals 0. This is my critical value. I'm only going to get one critical value here. 0 is their multiplicity 2. So x equals 0 or x equals 0. So I only write it down once. It's the only critical value here. So that means my number line is only split at the 0. So over here I had 2 critical values. This time I only have 1 critical value, so only 2 test points. So I'm going to do a test point of -1. Something over here, put it into the original, so 4 -1 squared greater than 0. Well, that gives me positive 4, and yes, 4 is greater than 0. And now I'll do a test point of 1, something over here. So 4 1 squared, is that greater than 0? Well, that gives me 4 again, and yes, that's greater than 0 as well. So they both worked. So what's my answer going to be? So I'm going from -infinity to 0, and this is strictly greater than, right? So this 0 is not going to be included. So it looks like my domain is -infinity to 0, parenthesis, and then union, parenthesis, 0 to infinity. Oh, that was kind of tricky. So this all worked, and this all worked, but 0, because this is not greater than or equal to, it's strictly greater than, 0 does not get included. So what does this mean? The domain is everything but 0. Think about this. If I put 0 in there, 4 times 0 is 0, and I'm going to have a log base 7 to 0, and that's an issue for the domain of the log. We can't have a log of a 0. But anything else, positive or negative, when I put it in there and square, it's going to be positive. So I can see that that makes perfect sense. Everything but 0 for my domain. So now we're going to flip over to the back side, and we're going to go take a look at these last set of equations where we're being told some new rules on how to solve a log equation. We kind of did this a little bit with which one was it, 7 and 8 on the front side. So what if the equation is a log equation where it's a single log on one side and then a term that doesn't have logs or terms that don't have logs on the other side? So sort of like what I had when I rewrote number 7 and I wrote log base 1/3 of 9 equals x. I had log on one side and a term on the other side. And if that's the case, then one way, this is one way to solve a log equation, and it's when it's a single log and then term or terms that don't have logs in them on the other side, you can rewrite that in exponential form using the rule of how the pieces of the puzzle fit together. The base of the log to the power of the answer equals the argument of the log. So you can rewrite it in its equivalent exponential form and then try to solve that resulting equation. One comment I want to make here is that you need to remember, depending upon where the unknown is, like if it's in the base of the log or the argument of the log, you need to think about what's excluded in those. In other words, what are the restrictions? What's the restrictions on the base of a log? So again, I'm going to write it down one more time. Just keep in mind that base of a log has to be greater than 0, not equal to 1, and the argument of a log has to be greater than 0. So there are requirements or restrictions on a log's base and on a log's arguments. And so when I'm solving equations that involve logs, I always have to do a double check and make sure that I am respecting those restrictions. And if my answer doesn't respect those, then I have to get rid of it. So let's try this idea with number 1, where they've asked me to solve log base 3 of x equals 5. So this is a log equation because my unknown is either part of a base of a log or an argument of a log or an answer to the log. I see a log there. So then I see a log in an equation, it's a log equation. So how do I solve a log equation if I can't like put it into my calculator and let it do the work for me? Is I'm going one way of trying to solve a log equation, particularly if it's a single log equal to some term over here. I can use the definition of the log and rewrite it in its equivalent exponential form. So I'm going to try that. I'm going to rewrite in its exponential form, which says 3 to the power of 5 has to equal the argument, which is x. So I rewrote it in exponential form. Here it is. So now, what kind of an equation is it? Here it was a log equation, but now what kind of an equation is it? Don't tell me it's exponential. It's linear. Look at where the x is. X equals. I'm almost done. I just have to go figure out what 3 to the 5th is. So x is equal to, this is linear. What is 3 to the 5th? So let's see. 3 squared is 981 times 3. So 243. And I'm all done. So sometimes being able to rewrite a log equation in its equivalent exponential form can help me to be able to actually solve that log equation. So if I look at number 2, I've got a log equation again. As I start writing this, I can see that it's a log equation. I have a log. The base is 2. The argument is 2x plus 1. The answer over here is 5. And I forgot to do something here, so we're going to go back and look at this for a second. So x is 243, and I shouldn't have circled it yet. And here's why. Where was the x in this original equation? Where was the x? It was in the argument, right? So I just lost a point on this problem. It was in the x. And what do we know about the argument of the log? Argument of the log has to be greater than 0, right? So if x is 243, is the argument greater than 0? Yes, so we're good. I need to see that you check this, okay? So the fact is, the argument, which is x, is greater than 0, so we can leave that answer. It's perfectly fine. It does not violate any of the restrictions on the argument or the base of a log. So now we'll go to the next one. Again, I have a log equation. It is a single log equal to a term over here. So I'm going to try to solve it by rewriting it in exponential form. So I rewrite in exponential form. I keep abbreviating more and more here. So this says 2 to the power of 5 is equal to 2x plus 1. What kind of an equation is it now? There's the unknown now. It's linear. I know how to do this. Well, first I need to go figure out what 2 to the 5th is. That's 32. Equals 2x plus 1. I'll subtract 1. I'll get 31 equals 2x. I'll divide by 2. So I get x is equal to 31 halves. So now, it was a log equation. Where's the x in this log equation? It's in the argument. So you need to go and check and make sure that the argument is greater than 0. So now I have this was the argument, so it wasn't hard to check. I have a little more checking to do here. In other words, I need to make sure that 2 times 31 over 2, which is what x is, plus 1 will be greater than 0. And yes, it's going to give me 32. So yes, it is greater than 0. So I can now go and circle my answer and feel good about it. Let's see, number 3. So I've got log base x of 81 equals 2. They're asking me to solve that. That's a log equation. Single log equal to a term over there on the other side that doesn't have a log in it. So I'm going to try and rewrite it in exponential form. So I'm going to write x to the power of 2 is equal to 81. X to the power of 2 equals 81. Now what kind of an equation do I have when I wrote it in exponential form? It is quadratic. How many answers is this going to have? 2. This is set up perfectly for the square root property. So I take the square root, plus or minus square root. This gives me x equals plus or minus 9. So I get x equals 9 or x equals negative 9. So in other words, x equals 9 or x equals negative 9. Why am I bothering to write those out instead of just circling this? Because now I'm going to go check. because I think I remember the x being somewhere where I have to be careful. The x is in the base. And what do you know about the base again? The base of a log needs to be greater than 0, not equal to 1. What does this one work? 9 is, because it's just x there, so 9 is greater than 0, not equal to 1. How about negative 9? It's not greater than 0, so it's gone, because it's violating the rules of the base, so the only answer here is x equals 9. So be careful with that. Sometimes you have to get rid of some of your answers. So we'll go take a look at number 4. So we've got log at base 6 of 36 equals 5x plus 3. So this is a log equation. I've got a single log and then terms over here that don't have logs in them. So I'm going to try and rewrite this in exponential form. So I'm going to write 6 to the power of 5x plus 3 has to equal 36. 6 to the power of this whole thing over here has to equal 36. What kind of an equation do I now have? It's exponential, isn't it? So how do I solve an exponential equation? The only way we have so far is to try and create same bases. The base here is 6. The number here is 36. Can I create a base of 6? I think I can. 6 to the 5x plus 3 equals 6 squared. So now what do? Drop the bases, equate the powers. So 5x plus 3 equals 2. Now it's linear, so I'll subtract 3. I'll get 5x equals negative 1. I'll divide by 5. So x is equal to negative 1/5. Before I circle it, I'm going to go look and see where the x was, because this was an original log equation. The x, oh look, it wasn't there or there, so this can be anything. It's just the base of the log and the argument of the log that I have to be careful with. So I'm good. This is my answer. X is equal to negative 1/5. So just be careful when you're solving these. If the x is in the base or in the argument of the log, then you're going to have to check it and make sure that it satisfies the restrictions on that base or on that argument. So I think I'm out of time, so I'm going to stop there. We just have a few more problems to do to finish this section, and then next time we'll do that and we'll move on to 6.5. So I'll see you again on Thursday.